The night sky of late 2025 has offered humanity a spectacle that is as beautiful as it is scientifically profound. The arrival of Comet 3I Atlas, only the third confirmed interstellar object to traverse our solar system, has turned the gaze of the world's telescopes upward, reigniting a fervor for understanding these icy wanderers. While its alien beauty captivates the public, for planetary scientists, 3I Atlas is more than just a light show. It is a data point from the other side of the galaxy, a frozen messenger that, when read in conjunction with our own local comets, is rewriting the history of how worlds are made. For millennia, comets were viewed as omens of doom, hairy stars that foretold the death of kings. Today, we know them as the frozen leftovers of the solar system's birth, time capsules that have remained largely unchanged for 4.6 billion years. They are the Rosetta Stones of astronomy. By studying comets, we are not merely studying chunks of dirty ice. We are performing celestial archaeology, digging into the primordial dust that coalesced to form the Earth, Mars, and the gas giants. In this episode, we are going to explore the latest discoveries, from the dark comets hiding in plain sight to the complex organic chemistry that suggests comets may have seeded life on Earth, uncovering the violent, chaotic history of our planetary origins. The discovery of 3I Atlas in July 2025 marked a watershed moment in planetary science. Unlike the erratic tumble of Oumuamua in 2017, or the ghostly apparition of 2I Borisov in 2019, 3I Atlas has provided an unprecedented wealth of data due to a coordinated dragnet of observations from missions like the Jupiter Icy Moons Explorer, Psyche, and the James Webb Space Telescope. What makes 3I Atlas truly revolutionary is its composition. The infrared eyes of the James Webb Telescope pierced through its coma to reveal a chemical fingerprint that is distinctly alien. The comet possesses a carbon dioxide to water ratio significantly higher than almost any comet native to our solar system. This dry ice dominance suggests that 3I Atlas formed in a stellar environment vastly different from our own, perhaps around a cooler, older star, or much further out in its home system's protoplanetary disk, where carbon dioxide could freeze out in abundance while water remained scarce or locked in other forms. Furthermore, the detection of nickel and iron vapors in its wake, an anomaly first puzzled over in solar system comets, was present in 3I Atlas, but in ratios that defy our local standards. This hints at a metallicity in its parent star system that could be twice the age of our Sun, offering us a glimpse into the chemistry of the galaxy billions of years before Earth even existed. Perhaps the most visually stunning revelation has been the observation of cryovolcanic eruptions on 3I Atlas. As it approached perihelion, the comet did not just sublimate evenly, it erupted. Jets of gas and icy dust blasted from its surface, indicating a complex internal structure. This activity suggests that cometary bodies, regardless of their origin, share dynamic geological processes. It implies that the mechanism of building planets, specifically the accretion of icy pebbles that trap volatile gases, is a universal constant, though the flavors of the ingredients may vary from star to star. To understand why these objects are so critical to planetary science, we must look back 4.6 billion years to the solar nebula. Our solar system began as a giant, rotating cloud of gas and dust. As gravity collapsed the center to form the proto-sun, the remaining material flattened into a disk. In the hot inner regions, only metals and rocks could withstand the heat. These became the terrestrial planets: Mercury, Venus, Earth, and Mars. But beyond the frost line, roughly where the asteroid belt sits today, temperatures dropped low enough for hydrogen compounds like water, ammonia, and methane to freeze into solid ice. Comets are the survivors of this cold outer realm. They are the planetesimals that never grew up. While their siblings collided and merged to form the cores of Jupiter, Saturn, Uranus, and Neptune, comets were the debris left scattering the construction site. This preservation is key. Earth has melted, differentiated, and resurfaced itself countless times through volcanism and plate tectonics, erasing almost all geological record of its birth. Comets, however, have spent most of their lives in the deep freeze of the Oort cloud or the Kuiper belt. When we sample a comet, we are sampling the original mix of gas and dust that existed before the planets formed. This brings us to one of the most enduring mysteries in planetary science: the origin of Earth's water. The early Earth, molten and bombarded by radiation, was likely too hot to retain vast oceans. Water must have been delivered later, a late veneer brought by impactors. For decades, comets were the prime suspects. They are, after all, dirty snowballs. However, the smoking gun for the source of Earth's water is the deuterium to hydrogen ratio. Deuterium is a heavy isotope of hydrogen. Earth's oceans have a specific ratio, and if comets delivered our water, their ice should match this chemical fingerprint. For a long time, the data was discouraging. Missions to Halley's Comet and measurements of Comet Hyakutake and Hale-Bopp showed deuterium ratios twice that of Earth's oceans. This suggested that comets were not the primary source, shifting the focus to carbonaceous asteroids. However, the story has become far more nuanced in the last decade. In 2011, the Herschel Space Observatory found that Comet 103P Hartley 2, a Jupiter family comet, had a deuterium ratio perfectly matching Earth's. Conversely, the Rosetta mission found that Comet 67P had a ratio 3 times that of Earth, the highest ever measured. Then came the hyperactive solution. Recent studies, including observations of Comet 46P Virtanen, a hyperactive comet that releases water from icy grains in its coma, also found Earth-like ratios. The discrepancy suggests that not all comets are created equal. We now believe there were distinct reservoirs of ice in the early solar nebula. Comets forming near the giant planets might have different isotopic signatures than those forming further out. The hyperactive comets, which often contain Earth-like water, might represent a population of ice-rich bodies that formed just outside the snowline, the perfect location to source Earth's water. This leads to a compelling synthesis. Earth's water likely came from a mixture of sources. While asteroids provided the bulk, a specific class of comets contributed a significant fraction, perhaps delivering the final topcoat of volatiles that made our planet habitable. In 2024 and 2025, a new class of object moved from theoretical fringe to observational reality: dark comets. Astronomers identified 7 enigmatic objects that appeared to be asteroids, showing no tail and no coma, yet their orbits decayed in a way that gravity alone could not explain. This non-gravitational acceleration is a hallmark of comets, caused by outgassing jets acting like thrusters. These dark comets are likely the shriveled husks of comets. They have a crust of dust thick enough to hide their ice from the sun, preventing the formation of a visible coma, but thin enough to allow small, invisible jets of gas to escape. This discovery has profound implications for planetary origins. First, regarding water delivery, if dark comets are common, the amount of water available in the inner solar system during the Late Heavy Bombardment may have been vastly underestimated. We might be sitting in a graveyard of dead comets that dumped their oceans onto Earth billions of years ago. Second, regarding planetary defense, these objects are darker and harder to spot than active comets. Understanding their population is crucial for protecting Earth from future impacts. And third, for future space exploration, dark comets represent accessible reservoirs of water and fuel in near-Earth space, masquerading as dry rocks. If water provides the stage for life, organic molecules are the actors. Here, comets have provided the most startling revelations. We have known for years that comets contain simple organics like methane and ethane. But the Rosetta mission detected glycine, the simplest amino acid, and phosphorus, a key component of DNA and cell membranes, in the haze of Comet 67P. More recently, the 2024 study on peptides has shifted the paradigm. It was previously thought that complex peptide chains, precursors to proteins, required liquid water to form. However, laboratory simulations of the cold, vacuum conditions of interstellar space, conditions found in the cometary formation zones, proved that carbon atoms can link up to form peptides on the surface of dust grains. This implies that comets are not just delivery trucks, they are chemical factories. During their billions of years in the cold dark, radiation processes simple ices into complex prebiotic molecules. When these comets impacted the early Earth, they didn't just bring water, they brought a starter kit for biology. The Late Heavy Bombardment, roughly 3.9 billion years ago, often viewed as a cataclysm that would sterilize the Earth, might have actually been the biogenic event. The heat of impact could have provided the energy for these cometary peptides to assemble into the first self-replicating structures. Comets also serve as the tracers of the solar system's dynamic history. The fact that we have 2 distinct reservoirs, the spherical Oort cloud thousands of astronomical units away and the flat Kuiper belt much closer, tells a violent story. Theory suggests that Jupiter didn't stay put. In the Grand Tack model, a young Jupiter migrated inward toward the Sun, clearing out the early asteroid belt, before being pulled back out by the formation of Saturn. This plowing motion would have scattered water-rich planetesimals inward, drenching the dry proto-Earth. Later, the giant planets likely engaged in a gravitational dance known as the Nice model. Neptune and Uranus were likely pushed outward into the primordial Kuiper belt. This disrupted the stable orbits of millions of icy bodies, scattering them like billiard balls. Some were thrown inward, causing the Late Heavy Bombardment. Some were thrown outward, forming the scattered disk and the Oort cloud. Some were ejected from the solar system entirely, becoming interstellar vagabonds like 3I Atlas. The comets we see today are the survivors of this celestial game of pinball. Their current orbits are the scars of these ancient planetary migrations. As we close out 2025, the future of cometary science is brighter than ever. ESA's upcoming Comet Interceptor mission, launching in 2029, will park itself in space and wait for a pristine, long-period comet, or perhaps another interstellar visitor, to enter the inner solar system. It will then ambush the target, studying a body that has never been altered by the sun's heat. Furthermore, while missions like Stardust brought back dust, Future concepts aim to bring back cryogenic ice samples. Analyzing the intact ice structure would reveal the spin temperature of the formation era, acting as a thermometer for the solar nebula. And with the peptide discovery, the search for life beyond Earth now includes comets. Could the deep interiors of comets, warmed by radioactive decay, harbor liquid water pockets and primitive chemistry? Comets are far more than dusty snowballs. They are the narrators of our history. They tell us that our solar system was not built in a quiet, orderly fashion, but in a chaotic storm of migration and collision. They tell us that the water in our glass and the carbon in our cells may have been forged in the dark reaches of space, delivered to us by these cosmic messengers. As 3I Atlas fades into the dark heading back to the interstellar void, it leaves us with a humbling realization. We are, in a very real sense, the children of comets. We are made of the star stuff they carried, living on a world they watered, looking back at them to understand where we came from.